Welcome to another data science deep dive on our technical track. In the following session, Barak Krakauer, data scientist at Levi's, shares how Levi's is using machine learning to determine the assortment of products at Levi's stores. Enjoy.
Hi, so my name is Barak Krakauer, and I'm going to be talking today about building and interpreting models for product assortment. So let me start by introducing myself. So again, my name is Barak Krakauer, and I'm a data scientist at Levi Strauss & Company. I've been a data scientist there for about 2 years, and before that, I worked at IBM. I was doing data science work at IBM with other companies as well. And prior to that, I actually have a background in academic philosophy where I studied logic and language and worked a lot on issues related to philosophy of language that I carry forward now as best I can into data science work. So I do a lot of natural language processing stuff and things like that. This particular project has bits of NLP, but it's mostly about product assortment, what we call it in-house micro assortment. And so the project that we're talking about today is around figuring out how to stock a store. So Levi Strauss, we have a number of stores around the country and around the world. We have outlet stores and we have what we call mainline stores, which are kind of the branded stores where we sell kind of the more top tier end of our product line. We are, even in the midst of the pandemic, we're in the process of opening about 100 new stores over the next couple of years in the United States and a bunch more around the world as well. And we're trying to use increasingly data science to figure out where to open stores and how to stock the stores. So for each new store, we want to figure out how best to assort that store in terms of the products based on what we think is going to sell well there. So that's, of course, going to depend on historical data, customer data, product data, forecasts, all sorts of things like that. And so putting this all together, we want to know if we're opening up a new store in a particular location, which exact products, which exact SKU should we put on the shelf in order to best figure out what do you think we would sell? What's the assortment look like based on what will sell well and what will combine with other things? That's essentially what this project is. So part of what I want to talk about is how we built this kind of model to predict how things will sell and what things we should stock in a store. But part of what I want to talk about as well, kind of at a more meta level, is interpretability, because we built into this project from the beginning this idea that the model should be interpretable. We should be able to figure out why it's saying what it's saying, and then use that to kind of help start conversations with other parts of the business. So at a data science level, the question is, how can we build this model to figure out what we should stock in a store? But at a business level, the question is, how can we then use this model to really kind of justify what we're saying, to determine marketplace insights, to really kind of drive things forward in a way at a much kind of higher and broader level than just a narrow level of figuring out how to assort the store. So as I mentioned, Levi's is going to open up a whole bunch of new stores in the next 2 years. And these stores are going to be smaller footprint, but they're going to be an important aspect of how we position our products, how we kind of define and think about the brand. And it's going to be also important because an increasing percentage of Levi's business is coming from direct to consumer, which means the website and our own stores, as of course, wholesale is getting increasingly challenged. So given all of this, given that we want to kind of maximize the benefit of doing this, the question is, how can we use machine learning to determine how we stock these stores? Can we customize an assortment for a new store based on what we know about the weather, about the shoppers, about trends, any other kind of data that we have? So at one level, how do we figure out how to stock these stores? But another level, what can we learn about our customers more broadly by doing this? So the things I want to build into the model from the beginning, from the get-go, we want it to have the model be interpretable. We want it to be able to kind of come to a planning or a purchasing team with what the model is saying, but in a way that we can query the model and figure out why it said that. Because if there's a disagreement, we want to be able to kind of figure out why and figure out if the model is right or if they're right, and kind of have the conversation go deeper than just a simple model output. Ideally, we want to have product insights. So if the model is really keen on a certain kind of product or a certain family of products, we want to know why, because that's super interesting for the sake of, being able to further double down on what that kind of product line is, why it's doing so well. It'll help us figure out maybe to make more of it or maybe to target a certain area or something like that. And of course, we want the model to be simple. for a number of reasons. Part of it goes back to interpretability and explainability. Part of it goes back to kind of scaling and maintenance issues. But in an earlier version of the model, we just had this approach of like throw whatever data we can at a big algorithm and see how it works. And we want it to be a bit more thoughtful than just doing that. So these are kind of the desiderata going in of how we want this kind of project to look. So the question then is, how do we build this model? So we want to predict how a product will perform at a store. And as you might be able to tell from the image, we had decided to go with Cat Boost. Cat Boost is a gradient boosting model. So for the people on the more technical end of things, this is a kind of tree-based model where we look at the errors from kind of previous iterations and build trees around trying to best figure out how to figure out what the prediction for how well the product is going to do is going to be. The reason we chose this model, this version in particular, Cat Boost, is it does well with categorical features. So what I mean by that is one of the most important bits of data that we're using for the model is product features. So these are things like, a description of the neckline for a top. So if we're talking about jeans, we want to talk about what the leg opening is like or what the thigh is like or things like that. And these are all categorical features because we have a table that has her product, different kind of features about it. And we want to know based on the leg opening, based on the color, based on whatever, how is it going to sell? And because that's going to be such an important part of it, we want to make sure that our model is one that really handles this kind of thing intelligently. So again, for people on more technical end of things, they might know that if you have a lot of features like these categorical features, if you're not careful, the model is going to overfit because you'll have a lot of ways of cashing out what it means to have a different kind of leg opening or a different color, something like that. And so Cat Boost is good because it's kind of built from the ground up to work well with these kind of categorical features. We also want a model that's readily interpretable, and Cat Boost does that. Cat Boost has built-in support for SHAP values. And so we'll come back to it later. So if you're not familiar with this, we'll talk about this kind of toward the end. But this is an important part of interpretability. We want the model to be such that it has this built-in way of interpreting it in a way that goes beyond just kind of spitting out some kind of number, but you can figure out how the contribution of each feature to the revenue prediction for that product. And, the Levi's data science team is very big in cats. So we think that a major feature of the Cat Boost model is that it has cat in the name and allows for a lot of puns, which throughout the development of this model kept us kind of amused. So that's the kind of model that we struck with from early on. We also were gathering data sources. And so this is not an exhaustive list, but this should at least give you kind of a sense for the kind of data that we're working with. Some of it is store data, by which I mean we have existing stores. And so we want to figure out how products are selling in existing stores. We have user demographic data. So by that, I mean we have the kinds of people who live in the area that we're opening up new stores. We want to look at those people. We have localized e-com data. What I mean by that is we have, of course, our website, levis.com, and we can figure out if we're opening up a new store within a certain radius of that new store. We look at all the transactions that go to the zip code of that new store and use that e-com data, at least in part, as kind of a proxy for how people in the area would shop. There's some complication there because obviously the e-com shopper might be different from the person who goes to the store to shop in various ways that we try to maybe correct for. And there's a kind of question about tourists. So we have some stores in heavily touristed areas that might not be as amenable to looking at e-com data to figure out. But that's kind of our first pass of looking at how something will sell in an area is that e-com data localized to that area. We also have weather data. So if you're looking to open up a new store, we want to know what the weather's like there, how hot it is, precipitation, things like that. We have wholesale data, so we know how things are selling in stores that sell Levi, so not Levi stores, but we still know how things are selling at local Target or Urban Outfitters or whatever, and we can use that to help inform how things are going to sell at a Levi store. And as I was mentioning, product data. So this is just data about particular products, about their cut and color and shape and things like that. And so this is, again, not an exhaustive list, and in some cases, these kinds of sources are kind of spliced together, but that's a sense for the kind of data that we have that are going into this kind of project. So once we do this, we then derive an assortment by looking at the revenue predictions that we have. So we'll have a given SKU or a given SKU, and then we figure out what the model says the revenue for that is going to be. We don't just want to stock a store full of the highest revenue predicted products. We want to have there be a diverse and interesting selection of products. So for instance, even if we think that like dark blue indigo will sell the best, if the entire store is dark blue indigo, that's not the kind of look that we want. Or even if we think that jean jackets will sell the best or have highest revenue, we don't want to stock a store entirely full of jean jackets. So we kind of weigh the revenue predictions against a diversity measure to assure that we have coverage across our different product categories, across different colors and things like that. So it's not a single objective function in terms of looking just at revenue prediction. We also want to look into these kinds of things that look into make sure that we have a diverse assortment, an assortment that matches the distribution that we would see in terms of other stores about what kinds of products we sell in those stores. So that's an overview of how we built the model itself. But arguably the more interesting question, I think, is how do we interpret the model? That was one of the things we were building in from the beginning. And so we have the SHAP package uses the shapely values to compute the explanations looking at the contribution of each feature. So what that means is we have this list of features. We want to know which feature is doing what revenue prediction and to what degree. So some feature is going to drive the revenue prediction up compared to some kind of dummy value for that, and some would drive it down given some dummy value. And so we want to know the contribution of each one. So for instance, if we have a prediction for a pair of shorts that is selling at a certain place, we can use it to see how the weather at that location, if it's a hot area, how the weather is contributing to that revenue forecast, separately from the color and separately from how similar products look at other stores or things like that. So this is some kind of sample output from the model looking at what we call PC9, so looking at SKUs, looking at SKUs of different products. And I have here two examples. So one product was selected by the merchants, by the people kind of assorting the store by hand, but not by the model, not by the automatic way that we're doing it here. And so we can see here this kind of just as an output of some of the top features and which way they're going. And on this graph here, the blue bar is going to the left to mean that these kind of features are actually driving revenue prediction down, whereas the red ones are driving revenue prediction up. And what's interesting about this product is that when we look at similar stores, so we look at a kind of store that is similar in way, we can spell it later, to the store that we're opening now, this product is actually not selling well at that similar store. So the model is not very keen on that kind of product, even though it is selling well in e-com. That you can see is driving the prediction up. And then we see other things like temperature, things like that, driving prediction down and so on. And so this lets us talk to the merchants and say, we have this kind of output from our model. We think it's working this way. We can justify it. We can talk about it. And then we can do a deeper dive and try to figure out, who's right. Obviously, in some cases, the model might be wrong. There might be a bug in the model, or it might just be looking at the wrong kind of thing. But again, this lets us have a more interesting conversation with outside stakeholders than just, oh, look, it's a big number. You should trust our model. Like that's obviously not going to fly very far in this kind of world. Another example is below it. This is a product selected by the model, but not by the merchants. And what's interesting this time is the number one feature, and by quite a bit, is MSRP. And this we thought might have even been a bug. Like this sounds like the model's overfit. If the thing that we're really sure is making this a good bet is the pricing, maybe something's gone wrong, but we want to take a deeper look into it. And so again, we have an interpretable model. It gives you the option to debug it and to do a deeper dive in a way that you might not get if you weren't building in interpretability into your model in this way. And so in this case, we did a deeper dive into it. And so what we're doing here is, this is looking at a certain kind of slim taper cut. We can do what this is basically a partial regression plot of looking at this thinks that price is so important to the revenue prediction, like let's actually look at that. So we then fed the model some different possible MSRPs and saw how the model spit back revenue predictions based on the MSRP. The thought was if this graph looks really messy and weird, it's a bug. It's overfit somehow, like there's something crazy happening and we should kind of back off. But what we see here is actually a really sensible looking curve where there's kind of a sweet spot in price. And when you get the pricing right, you get a lot higher revenue. And so there's actually a really, really sharp peak here, which might even explain why the kind of shape value for MSRP was as sharp as it was as big as it was. And so what we get out of this is, again, if we trust the model, not only do we have this explanation for why the price was so important here, but we might even have a tool that will let us set the prices going forward for new products. Again, I don't want to press this too far because, there's a lot more work to do to verify the model, but this is kind of another benefit you might get from thinking about it this way is that you can then use these kind of shape values and these kinds of model explanations to really push even farther into market insights and pricing. Or this is another kind of example in color. So what this is doing, this is another kind of model output looking at this class of woven shirts. And these are, again, the top features. I kind of unblurred some of them. The interesting ones, at least from the perspective of our project, are ones that are toward the top, the higher kind of more important features, as well as the ones that have kind of a wide range of different model outputs. So each dot in this is a single product. And so what you're looking at here is, for example, in color family, we have a single dot that presents a single shirt. And in some cases, the color of that shirt is making the revenue prediction much, much lower. But in other cases, if we go more toward the right, that dot is kind of toward the right, and that means that the color of that shirt is making the revenue prediction significantly higher. And that's interesting. I mean, there's other things we got with too, like store revenue is kind of clumped together, so that's not really a big issue. Neckline does matter, so neckline is an important feature. But let's look at color for this example. What we find is that the color matters a whole lot. In some stores, if a shirt is red, for example, that's going to be a huge, huge barrier to it selling well. Like this graph is showing us some different stores. And toward the left, there are shirts that are red sell only a quarter as well, 25% as well as a blue or black or neutral shirt. Whereas other stores, now we're looking toward the right, they sell better. And so what this is telling us is, if you think about the color of a shirt, if it's a red or some other pop of color, whether or not it's going to sell well is not a binary thing, but it really, really depends on the store. So this is getting back to the strength of the micro assortment project is, if you're stocking a particular store, you want to know if it's an area where these pops of color shirts will sell very well or very poorly. And in the case of the store that we're looking at right now, we determined it was going to sell poorly. And this was backed up by the idea that these similar stores were more toward the left end of this graph, that these were stores where red shirts were not selling well, whereas in other cases, in other parts of the country, these shirts sell better than the more neutral shirts. So that's super interesting to us. So kind of in conclusion, the interpretability part of this is really important, because having this interpretability is essential for debugging and improving the model. If you think there's a problem, you can actually figure out why the model is saying what it's saying and look into that deeper. It's super important to communicate to outside groups about why our model behaves as it does, because having this kind of interpretability lets you really have these in-depth conversations about products and customers and so on. These insights and about our customers and how they shop will then drive decisions going forward in terms of the company, in terms of not just assortment, but how we produce products, how we market products, and so on, which is going to be important going forward for how we think about not just assorting stores, but how we produce and purchase products. So this is an example of what data science is doing, having implications for all across the company. So thanks. If you want to contact me, again, my name is Barak Krakauer. My email address is up here. Definitely happy to talk about questions or anything like that, but please feel free to reach out. I really, really appreciate it. I'm happy to do this. Thanks.
That was Barak, Krakauer, data scientist at Levi Strauss, talking about how Levi's uses machine learning to determine the assortment of products in their stores. If you'd like to watch more content like this, you can subscribe to the DS Insider program, where you see our complete on-demand video repository from a wide range of topics. Subscribe now by following the link in the video description below. Thanks!